It might be easy for you to tell that this is a dog and this is a cat. But how can a computer do this? Hello, my name is Isabela, and today I'll be telling you how I created a convolutional neural network to identify objects in an image. Don't worry, before we get into this, I'll explain what I'm talking about. First, we have to understand the image itself. Colored images are made of 3 different images stacked on top of each other. A red one, a green one, and a blue one. And of course, each of these is made of pixels. Now, let's talk about neural networks for a moment. Neural networks are a group of algorithms that mimic how the human brain functions and processes data. They're really a bunch of mathematical functions that take in an input, modify it many times, and create an output. Neural networks are made of something called neurons. Each neuron represents a mathematical function that takes in data from the previous neuron, transforms it, and passes it on to the next neuron. But for analyzing images, we're talking about a specific type of neural network. It's called a convolutional neural network. A convolution is basically taking a filter to detect patterns in an image. So a filter is a 3x3 pixel block that resembles a specific feature. It can be a line, a curve, and as we slide the filter across the image, a score is produced based on how well the filter resembles that section of the image. Using filters, we detect patterns to then detect objects. For example, when looking at a house, we may try to look for patterns like a door, a chimney, or a window. Any pattern that makes the house, well, a house. Computers don't detect the same features as we do. Computers learn to detect patterns by themselves to recognize what it is that the image has. To be processed by a neural network, images have to be converted into numbers. Let's go back to the idea of red, green, and blue that we talked about. Each pixel of an image is made of a certain amount of red, a certain amount of blue, and a certain amount of green. So we can basically represent any image with 3 huge tensors, or a grid of numbers, that represent the amount of red, green, and blue each pixel has. So now let's see how we can detect an object in an image. For this case, we'll be using the CIFAR10 dataset. This is a set of 60,000 images. Each of them is 32 by 32 pixels, and it represents one of the following categories: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, or truck. It's time for the code. The first step is downloading important libraries. I will import Torch, short for Pytorch, a framework that enables programmers to use tools and structures to build their AI models. It saves time and many lines of code. Inside Pytorch, I'll be using Torch Vision. This is to access the dataset and the computer vision utility. I'll be also importing Torch Vision.transform, which allows us to transform and manipulate the images. Finally, I'll import NumPy, which is a library that allows us to process arrays and apply math functions to them. For our model, images will be converted into arrays and then processed. Moving on to step 2. First, it is a transform function to turn the images into numbers. As we said before, numbers represent each individual pixel. We also set the epoch number to 4, meaning that we will go through the whole entire dataset 4 times. The batch size to 64, so that after every set of 64 images, our parameters are updated at a learning rate of 0.001. Finally, we load the data and split it into training and testing. It's time for step 3, the neural network. We start by importing the neural network and neural network function libraries to access tools specifically for a convolutional neural network. We use torch.nn.module to have a blueprint of a neural network to build on top on. We initialize the neural network and create the convolutional layer, pooling layers to make the image simpler, and linear layers to perform the prediction. Now that we have the layout of the neural network, we create a function to actually make the prediction. After each of the layers, we pass the output through the ReLU activation function, which is a function that converts all the negative numbers into 0. The output of all this process is 10 numbers. It is a score of how likely the image is to belong to each of the classes. After obtaining our score, we will set our optimizer and criterion functions. The criterion calculates the difference between the predicted values and the true values using cross-entropy loss. The loss is basically how good our model is at performing the task we want it to perform. The optimizer is stochastic gradient descent, which is used to adjust the parameters to make better predictions. Gradients show us the direction in which we have to adjust the parameters for better prediction. Now comes training. We will now be using our criterion and optimizer functions. We will be doing the predictions for the labels of the images, calculating the loss and the gradient, performing backpropagation to adjust the parameter, and repeating this training process for each of the 4 epochs. After going through training, the model has gone through 50,000 images 4 times. It's time to test it. We will keep track of the number of correct predictions and total amount of predictions using dictionary. We perform the prediction and output a tensor of 10 numbers, 1 for every class. And the class with the highest number is basically the prediction of the model. We will compare the prediction to the actual label and determine if it's a correct answer. Finally, we go through all of our testing data and we have the accuracy of our model. This was the accuracy of the model. I know, the numbers might not be too high. But the whole aim of this video was not to learn how to classify images of the CFAR10 dataset. The whole aim of the video was to learn how to build a model from scratch. So I hope that you enjoyed the process as much as I did, and I hope you learned maybe a little of how this process works. As you can see, if I, knowing no code, can create a model to classify these images, imagine what can be done with computer vision. It's insane.